Hi, everyone. I'm Max, and today I'm going to present some joint work with Kevin Jameson, who is just starting faculty at University of Washington, and my advisor, Ben Recht, at Berkeley. The talk is kind of going to be a mix of some new results and some more expository material about adaptive sampling. So at a really high level, I'm just going to breeze through this because you're probably familiar with it. In passive sampling, you treat data as given to you in some way. Maybe it's IID, maybe it's a time series which you don't have control over. But in adaptive sampling, we're going to use past data to decide how we collect future data. Think of it as sequential experiments being conducted. And obviously, this is a stronger model, so we might expect some improvements in overall sample complexity, but we need to be very careful because there are many classical examples where we can run into issues with consistency or robustness. And actually, today's talk is going to focus on lower bounds, and this isn't just because we're pessimists. Actually, in adaptive sampling, because you're aggressively leveraging assumptions about your model, analysis plays a really big role in algorithm design. Oftentimes, adaptive sampling can lead to really unintuitive sample complexities. And so what you do when you prove lower bounds is you might kind of break the problem up into smaller pieces, which kind of tell you what necessary steps need to be taken, and ultimately this can be used to design algorithms. Today we're going to work with a variant of the multi-arm bandits problem. You have a set of actions, 1 through n, and each action has a reward distribution, and because we're working with lower bounds for simplicity, we'll just say that the rewards are Gaussian with variance 1. And unlike the standard problem, we're going to assume that the vector of means lies in some constraining set. So our goal is going to be to leverage knowledge of the constraint set to identify the best action from noisy samples. Just fly, anyway. Rule of the game, we're sampling sequentially from time going through 1, 2, whatever. You're going to choose an action AT at each time. You're going to get a reward from this Gaussian distribution. And then at some stopping time, you're going to end the game, return an estimate of what you think the best action is, and we want this sort of fixed confidence guarantee. You can think of it as 0 delta pack. Just make sure you don't mess up with probability greater than delta. But we're going to try to, maintaining this guarantee, we want to use as few samples as possible. So some examples are, if we have no constraints in the constraint set, we're just a standard best arm identification. If we say that, say, our vector has to lie in the image, wow, this flies really aggressive, has to lie in the image of some matrix, we get the linear bandits problem, which has kind of been well studied. For matrices which have binary entries, you can recover many problems that show up in combinatorial bandits. And maybe another setting that's been studied is you have feature vectors, and maybe the means are Lipschitz with respect to these features. So these are just a couple cases where constraints change sort of the problem parameters. So here's kind of the expository part of the talk. What's been studied thus far is something that we'll call the oracle strategy. So you can imagine that each ground truth might warrant a different sampling allocation. And we'll give a concrete example of this in a minute. But just taking that to be true, suppose that an oracle actually knew what this ground truth was. Then they might prescribe, you can consider what sampling allocation that oracle might prescribe. And this is actually kind of, in some sense, this is the best you could hope for, right? The oracle knows something that maybe the learner doesn't at the start of the game. And because of this, it's actually kind of very suitable for proving lower bounds because you sort of can't rule out that maybe you are this brilliant oracle. So a really nice formulation of this comes from Kaufman and Garivier, and a version of it was presented in last year's COLT. I'm going to explain what this is in a second, but the expected number of samples is a solution to this optimization problem. So let's just go through it. Each tau A is going to correspond to the number of samples from one action, and you're going to try to minimize the total number of samples. But you need to satisfy some guarantee, and what is that guarantee? For all alternatives, so for every other alternative in S, which has a different best action than the truth, what you need to do is you need to ensure that you've collected just enough information, and this is sort of a weighted KL divergence term, so that you can get this high probability of not confusing you and the alternative. So this is sort of an optimization program which you can use to kind of give a lower bound on aggregate sample complexity. And the way you should think of it is as sort of the best sampling allocation in hindsight. So you'll get some solution to this, and it'll also suggest kind of qualitatively how you should sample according to these tau A's. And Another way you can think of it is sort of how would I verify that in fact A star of mu is the true best action? Well, if you've put your samples here, you can kind of use it to refute any other alternative hypothesis in a binary hypothesis test. It turns out also that as you let delta get really, really, really small, and I have to emphasize really small, optimal algorithms are known which achieve this in a variety of settings, not just unconstrained multi-arm bandits. However, this can lead to some misleading things that we'll see in a second. Just for those that want to see the bandit's lower bound, what happens is you just vary each alternative mean independently, and you'll get, for each mean, you'll get the standard lower bound, which is sort of inverse KL times log 1 over delta. I'm rushing through this, but just in case you want to see it. And if you sum that up, you get this bound that the bandits people are very familiar with. But this isn't so important for the rest of the talk. All right, so when does the oracle strategy give you a really misleading picture? Consider the case where the means are known to lie in the simplex, just as a toy example. And suppose that you end up with a mean which is right at the corner. I know this would be like an n-1 or something, but whatever. And so you're right at the corner of the simplex. So what could you do? Well, you could just, if you were the oracle, you could just sample the first action. Because that you would maybe be able to tell with constant number of samples that this mu1 is greater than 0.5, and because of the simplex constraint, you would know that, well, no other mean can beat it. But no real algorithm can achieve this, obviously, right? You kind of would need to look everywhere at least once. You expect ON. So this is kind of an example of when there is really a big gap between learning how to sample and then taking advantage of a sampling strategy which can verify. So to remedy this, and then some other things that'll come after, we introduce a new proof technique, with the goal of which is to really go after how we're sampling, not just sort of the end verification step. So the motivating problem is just we're going to say that we know the means up to a permutation. So this is even easier than the simplex. If we can prove a lower bound for this, one will carry through to the simplex as well. And what do we know? By Garivier and Kaufman, you can show that if you look at the optimization, the oracle can just sample all the, put all the samples on, say, the best action, verify that it's slightly better than the second, and you end up with the sample complexity. There's also a similar regret result by Rigolet et al. And in fact, the above bound is also correct asymptotically. As you let delta get really small, there are strategies which can just verify this. But again, it's really weird because you have n different options, and somehow you're getting some sample complexity that doesn't grow with n. So here's what we show. If the means are known up to the permutation, then if you look at the total sample complexity, it's bounded by this term. So let me just explain it. You need to first randomly permute the arms. Otherwise, you would know where everything is. And you look at the expected number of samples under this random permutation. And what you find is that it actually agrees exactly with this up to constant factors with the lower bound for the unconstrained version if you take delta to be some fixed small constant. You can also add in the term from Kaufman and Garivier, and it turns out that you can get an upper bound that matches this really easily up to maybe some double logarithmic factors. So what's the proof framework? So I'm going to give you an example. Imagine that you have just two vectors of means, and you take kind of one of them as an order, and one of them you flip the jth and the first. So this is how the simulator works. You can imagine before the game all the samples are drawn. So you have your transcript of samples from mu1, your transcript of samples from muj, and then you're going to send it through Agent Smith. And Agent Smith is going to just screw with the samples a little bit after some point, so that if you don't really sample past that point, you have no way of distinguishing between this modified transcript and the original. So formally, the simulator is some way of defining this modified transcript. And for this problem, what we'll do is we'll take we won't change the transcript for anything that isn't the first or the jth action. We won't change anything for the first and the jth action before we've sampled from them tau times. And the rest of the time, we're just going to sample IID from the distribution of this first action. Okay? So just formally, this is what's happening. So what are two things we can see about this? The first is, unless action J is sampled more than tau times, the simulator doesn't affect the distribution of algorithm's behavior. The reason you can see this is it's not changing other arms, not changing anything that happens before time tau, and it's not changing the distribution of the first arm. You're just replacing some ID samples with other ones with the same distribution. The second fact is that the simulator puts a hard limit on the total amount of information. you can exactly compute the KL between these two modified transcripts, and that 2 should be outside, but you get what you'd expect for Gaussian KLs. So something that you realize is, therefore, if tau is really small, then until action j is sampled more than tau times, we can't distinguish between actions 1 and j. And roughly what this means is that you're equally likely to sample actions 1 and j at least tau times. Yeah, not super deep, but it's kind of useful because you're really pursuing the sampling allocation. It's important to note that this doesn't come up in passive sampling. In fact, in passive sampling, the sampling strategies are fixed. You don't have these issues. And so the takeaway is that in active learning, we need to consider any possible sampling procedure, but crucially, this doesn't mean any possible sampling allocation. Some sampling allocations can arise from real algorithms. In fact, example, sampling at the corner of the simplex. All right. So we're going to consider some more subtle things that happen. So the Oracle lower bound is based on a two hypothesis test, refuting one instance from the hardest alternative. We know this is really loose for complex problems. Simplest example is linear regression. So are there more subtle statistical effects, and maybe can our simulator framework capture them? So here's a result for best action, kind of a warm-up. Suppose that you have one action which is slightly above the others by a factor delta, or by an additive term delta. Then for any m between 1 and m with constant probability, there's going to be a random subset of m actions, and this subset will include the best one, which has to be sampled delta inverse squared log n over m times. So the first way you should think about this is like a converse to Gaussian order statistics, right? This is sort of, you expect that the mth largest guy should look like log n over m. And you have to take an average over permutations for this to be true. And so what's happening is roughly the active learning algorithm is adapting to how these order statistics. The proof, we don't have time to go into this, but you can actually plug in a Fano's inequality directly into the simulator, get this result out. And what's cool is that it shows that this Oracle strategy is actually insufficient, because somehow you need to place these additional samples in an adaptive way on the random subset of these m arms, which happens to fluctuate, as well as additional samples in the best action, which in the Oracle optimization problem you wouldn't really see. Lastly, this lower bound is actually useful as a primitive for proving some lower bound on hyperparameter tuning, and my colleague Kevin has forthcoming work which will use this. All right. So other things we considered is a k-subset selection problem. So it's very similar to multi-arm bandits. I mean, best arm identification, whatever, it's constraining set. Only difference is now we're going to identify the best subset of k, or equivalently the subset which maximizes the sum of their rewards. So here's a bound that's already known. One can prove it using the result in the previous slide. It was also known from Kalyana Krishnan. And again, you randomly permute the arms, look at the expected samples from the 8th action under this permutation. What do you get? This should just be the total sample complexity, not the one over the 8th. But you get basically the gap inverse squared times k log n plus n minus k log k. And roughly you should think of this as you're paying a union bound of log n minus k on the top guys and a union bound of log k on everything else. And this is already known, but what's really great about the simulator is actually we were able to prove this very, it turns out it's tight, this instance-specific lower bound. And it's a little complicated, but maybe what I'll say at a really high level is what active learning seems to be doing is trading off between sort of how many arms need to be union bounded and this kind of information theoretic gap. And it's really learning this instance-dependent union bound, which is kind of cool. The proof technique we think is also kind of interesting. You kind of actively construct kind of like a weird order statistic, and the way that you do this is using is kind of by tilting the distributions in some way that really resembles the proofs of the log Sobolev inequalities. So if anyone's kind of curious to see that, check out somewhere deep in the appendix in the paper. And there's also this result, or version of it, was simultaneously discovered by Li Chen and others at 17. But what's kind of a nice takeaway of this, I promised you that lower bounds inform algorithms. Not going to have time to go into the algorithm specifically, but what you notice is there's this top K algorithm that's been studied called LUCB, And what we were able to do is use our lower bounds to realize that maybe we could modify the confidence intervals in some intelligent way. And it turns out that this modification based on these lower bounds gives a minimax optimal version of this algorithm. We also did some experiments, believe it or not, and it is more efficient in practice as well. So this is the algorithm that we'd recommend you actually running on real-world data. And just to compare it from what people have done, there's another algorithm that gets even more fine-grained results and is also minimax optimal, but it runs on this medium. It uses a subroutine, which makes it kind of difficult to use in practice. And the practical algorithm that existed beforehand, it's not minimax optimal. So that's how it compares. So just to conclude, before this work, we only had these asymptotic upper and lower bounds, and they could give you misleading information for structure. So what we did is we proved the sharp lower bound for permutations, which kind of shows the gap between these things. We had this instance lower bound for K-subset selection. Some interesting results about converses to order statistics, and finally, a state-of-the-art algorithm for top K. So thank you. Questions?
Thank you. Are there questions?
Can you improve our almost in the fixed budget case for the case subset?
Please repeat the question.
We haven't thought about it.
Please repeat the question.
Oh, please repeat the question. The question was, can you prove something for the fixed budget case? I don't think so. I think that even instance-dependent bounds for the unconstrained fixed budget there's still some open questions in that, if I remember correctly, right? There was a paper by Locatelli last year which had a log n on some cases but not on other cases, and we haven't thought about that yet, but that would be interesting to pursue.
And then on the slide just before, you had why do you have mu is the same for all the top K? Is it just an example? Or
It's an example, yeah. It's an example for I don't know. Kevin made this slide. He thought it looked cleaner, but yeah, no. I mean, it works. It'll work. Non-Gaussian rewards, different means. It's just that the algorithm won't get this really kind of super sharp adaptation to this result in general, but it still gets the minimax rate.
okay, and just to clarify, in the fixed budget for the top K, we don't know any lower bound even at the corridor package. So it's not about shading off log factor. We really don't know who to lower bound in the top K.
Okay. So to repeat the statement is that for anyone who didn't hear, we don't know lower bounds for a fixed budget for top K, and that seems to be an open question.
Okay, another question? Yep.
So would there be a way to package the simulator construction into like an optimization bound like the Kaufman variation?
Possibly, but one that would be very, very uninterpretable. The thing is that you have so much freedom in how you choose how the simulator perturbs the samples. So you should, another way to think of the simulator is rather than doing lower bounds with IID sequences, you're doing lower bounds with independent but possibly not IID sequences, or even lower bounds with just some sort of stochastic sequences. And maybe you could phrase it in terms of a sort of an infimum over all measures on sequences, but it would be something that would be very, very hard to work with. And in fact, getting some of these lower bound, like getting some of these more nuanced factors, we didn't have a really clean, short way to do it. Like this proof kind of takes a lot of time. And the other result that also proved it also takes kind of a lot of time. So we don't have a clean packaged way to do that yet. But I mean, the results for the lower bounds for unconstrained multi-arm bandits, it took 3, 4, 5 years before you had a really elegant, quick way to prove them. The first attempts, it took a lot of work. So maybe there will be. I'm hopeful.
Okay, thank you.